So just to be certain that we're sort of talking about the same thing, what I mean when I say generic programming is that it's a means for specifying algorithms in terms of deferred types, types that we haven't yet specified. And then these algorithms are later instantiated or made concrete by providing actual types. And if you're less familiar with the topics, there can be some confusion between abstractions, such as what you get with polymorphism, and what I mean by deferred types here, but I don't want to spend a lot of time trying to make that distinction right now. And what I'm including in this definition of a deferred type includes things like rank and kind, and in some cases maybe length parameters, that in Fortran would generally be considered not to be part of the type, but definitely pose part of the challenge that we have when we try to make, say, an algorithm that works for any rank argument. So in this sense, it makes sense to talk about rank being part of the deferred type. Some simple examples that many of you will have run into at various points in your career. You'd like to write a swap routine, right? How many times you had to do t equals x, x equals y equals t, right? And you'd like to be able to not have to rewrite that for every single type in the world that you run into. And it turns out that there's no good way to do that for the most part. There's a few special cases where you can get a fair bit of mileage, but in general, you're stuck in Fortran to have to redo that each time. There's also a lot of times when you want to create an analog of a built-in intrinsic, the prototypical example being findloc. It seems pretty clear what you want findloc to do with your own derived type, but there's no simple way to write findloc once for each of the different types of types you might want to throw at a routine like that. Those of you familiar with containers, especially if you're familiar with C++, say STL, you might have wanted to create lists, vectors, trees, maps, sets for your own types, or even for intrinsic types, and didn't really have a good way to leverage the amount of investment. If you went all the trouble and defined an integer vector, you'd have to sort of repeat the code to do a real vector or your type vector. Now you can get very clever and use preprocessors and include files to get a lot of mileage, and I've done a lot of that, but it'd be really nice if we had first-class support for that within the language. All right, so now to get us going, let's just do a brief history of Fortran. And so being from, oh, that got cut off, that's unfortunate. Being from NASA, of course, I'm gonna start, before Fortran existed, way back in time. This is a picture from James Webb, just a shameless plug. Okay, all right, so the first Fortran standard, and indeed the first formal language standard of all, was Fortran 66. But since I wasn't born yet then, I'm not gonna say much about that. Fortran 77, which actually was the language I learned, introduced structured programming. Fortran 90 was the discovery of the shift key. Inside joke there, but if you look closely at the bullets, you'll figure that one out. But in all honesty, you could at this point also start introducing lowercase code. But it also introduced free source format, derived types, dynamic memory allocation. These are all very, very nice things we all like. Fortran 95 is this standard which a lot of us, I think, probably scratch our heads and say, oh yeah, there was a standard, wasn't it? There actually are some pretty good things in there, but I tend to think of it as just sort of quick fixes on Fortran 90, but it's not true. Like pure and elemental come from Fortran 95, at least if Wikipedia is to be trusted. Okay, Fortran 2003, that's where we got C interoperability and object-oriented programming, something I spent a fair bit of the last 10 years playing around with. And then Fortran 2008 introduced the ability to do parallel programming within Fortran. And then 2018, which is a fairly recent standard, introduced teams for co-arrays and introduced even more interoperability capabilities with C. And that brings us up to the present. All right, so what's going on now? So the standard we're currently working to release is internally codenamed F202X or 2020X. In all likelihood, that's going to be Fortran 2023, but in these slides, you'll still see me mostly referring to that as 2020X. When we started this process back in 2018, we surveyed a wide variety of Fortran users to find out what they wanted, and then the committee did a lot of analysis and prioritization. And what emerged from this process were two big priorities, and a whole bunch of other smaller things that we thought we could do sort of at the same time. One of these was exception handling, and that was assigned to the JOR subgroup, and the other was generic programming, which was assigned to the data subgroup. By the time we got to 2019, though, there were some problems. JOR subgroup was not able to find any consensus on what type of exception handling should be done, and some of them didn't seem like they'd be feasible with the constraints of the language as it was, and so they convinced plenary to actually drop that as one of the priorities. Just the reality, not everything we want to do can be done. The data subgroup did make some progress during this time, and I'll discuss a little bit more in some of the coming slides, some of the things that we did get done. But there was still a lot of rancor and internal debate about fundamentally different approaches to the problem. And I'm not going to spend a lot of time today talking about what some of the other approaches were, but be aware that they might have had the features appearing sooner, and so there's something to be said about getting the features sooner rather than later. At any rate, the full committee decided to do the approach that I'm going to be talking about today. And they also recognized that this harder approach would be difficult to fit within one release of the standard now that we're trying to do relatively short release cycles. And so a new subgroup was formed called generics with the idea that it would not aim for delivering something for 2020X, but instead 2020Y. And we're all really hoping that the second 2 in that doesn't become a 3. But anyways, so this generic group formed, they asked me to lead it, and we've been meeting online roughly once a week most of the time. After big meetings, we sometimes go a couple weeks without, and we've been trying our best to make progress, and it was slow going at first, but we're starting to get some inertia now. Okay, so what things are going to appear in 2020X that are related to generic programming? So one big thing is the ability to do rank agnostic array declarations. So if you look at the list of examples we see here, you can, there's my mouse, okay. So you can declare, I pulled these examples out, but I'm getting very confused. I want to come down to these examples down here. Let's look at the deferred shape ones. So I can declare this is the dummy art. I'm sorry, I'm getting myself confused by not having looked at these examples. I will have to confess this talk was put together fairly quickly at the last minute before I got on a plane. But basically what we now can do is we can declare the rank of an array rather than having to give its shape. So before where you would have done something like dimension of colon, comma, colon, comma, colon, you can now do rank of 2, like this, okay? All right. These can be dummy arguments. They can be deferred allocatable, deferred pointer. But you still, in order to really do a lot of things with generic, you're still probably talking about an include file in order to get overloaded for the different ranks. We also gave the means now to do rank agnostic access to the array elements. This is something which I'm sure many of you will have wanted to do at some point or another. You've got an integer array and you'd like to interpret it as the indices into a multidimensional array. Okay. Something you cannot do with Fortran, and the actual code you have to write is really tedious and verbose. We now have this at notation that allows you to do things like this. And a little bit more to the side of those issues, we also introduced the features of type of and class of. So once you've got some variable, you can declare additional variables to be of the same type, or to be class of, which means that they can be that type or any subtype of that type. Okay, so where we're going with 2020Y. So we have this generic subgroup, and we had to sort of prioritize our approach to dealing with this problem. So one issue that we try to keep in mind is efficient implementation. We want the things that we're going to be able to do generically to be as efficient as if they were directly coded for the actual types that are going to be used. We're also being driven by use cases that have been passed by the committee. We're trying to make sure that we don't do unnecessary things that aren't justified by the use cases, and we're trying to make sure that everything we do actually will allow those use cases to be coded when we're done. And of course, we want to be minimal and conservative. We're not overgeneralizing because that's going to make the problem too hard for the first go around. There's going to be things we're going to mess up. The narrower we define it, the more likely we can get it right. And of course, it has to integrate well with the existing features. Fortran is a language with a lot of history, and we can't do things which break with the past in any fundamental way. And we're learning from other languages and what they did, what they got right and what they got wrong as they did it. And what's been very helpful with us is we have an outside consultant, Magna, and I'm going to mess up your last name, but Havrayan, something close to that. I never have to say the last name, so I can't pronounce it. Anyways, he's been invaluable at helping us understand both why we want to do certain things and helping us to see past our immediate inclination as Fortran programmers. We sometimes have to teach him enough Fortran to say why we can't do something, and then he can come back to us and says, but then we could probably do this instead, and we make some progress. And one of the things that emerges from this experience with the languages, and I'll spend some time talking about this, is the notion of strong and weak concepts. And that's something which is a strong consensus of the subgroup we want to preserve in the approach that we're taking. So where are we in this process? So we have passed use cases papers, we have even passed a requirements paper, and we have a slew of specification papers that are on deck this week. They have not been looked at by plenary. They may not pass. They may require, almost certainly will require a lot of changes, but a lot of what I'm going to show you today is sort of based on that because that's subgroup's current best thinking. Once those go through, then of course we've got to actually write out the syntax, and then we've got to actually figure out the edits to the standard. Those of you unfamiliar with the standards process, we literally have to go through, page by page and say, this sentence needs a comma or templates, or an extra paragraph here to explain why this thing for templates happens here, as well as a section about templates themselves. That'll be straightforward, but all the other places in the standard that need small fixes because of the new feature, and that's going to be a lot of work. Okay, some caveats going into this. The syntax here, as I just explained in the previous slide, is notional. Nothing has been approved. Lots of things could change. I think some of what I'm going to say, there's a good bet it will look something like this if it survives at all, but other things undoubtedly will change. The examples here are, of course, simplified also, mostly to fit in PowerPoint, but also to keep it short enough for attention of an audience like this. But more complete examples can be found on the website that I give here, and there's also references at the end of the talk. I would focus on the things that are more recent, because this has been sort of a scratch pad as the committee has done its work. We threw some things out, and some of the older things may not reflect our current thinking. The more recent stuff, especially the stuff from the last week, is very up to date with what we're currently thinking. Okay, first big thing we're talking about here is a new construct called template. A template is something that has a name. It has a list of dummy parameters. We're calling them parameters, not arguments, to avoid confusion with subroutines and procedures that have arguments. A template parameter can be any of the three things I've listed here. They can be types, and I'll talk about what I mean by that, values, or procedures. But we're not allowing operators at this time. This is something even plenary hasn't quite seen yet, and I'll explain a little bit more why later, and it probably is a good question for afterwards if people really want to know. What can go inside of a template? So the kinds of things that can go inside of a template are a lot like the kinds of things that can go inside of a module. It can define a derived type, it can define variables, enums, it can define procedures, it can declare things to be public and private, and it can even contain other template definitions. Okay. Then there's the instantiate statement. This is the dual of it. So in order to actually create concrete realizations of the template, you use the instantiate statement. The instantiate statement names the template to be instantiated and passes actual parameters that correspond to the dummy parameters in the template. So a type spec corresponds to a type dummy argument. So what do I mean by type spec? So you could pass in an actual that is real, or you could do real kind equal 32. You could do integer. So all of these things are type spec, but it doesn't, it's going to still be a scalar, but it's going to be basically a type, intrinsic or derived type, possibly with a kind or length parameter. The constant expressions correspond to, actual arguments for value dummy parameters are constant expressions, compiled time constant expressions. So, and we're allowing those to be logical, integer, and character. And this too is narrower than what we presented at the last meeting to the group, and I can explain more about why we went restricted which kinds of things we're allowing there. Procedure and, boy, that's a typo there, so I apologize. A procedure, no, I got this right. One moment. Procedure and operator actual arguments correspond to procedure dummy parameters. This sounds a little bit funny because how can an operator actual parameter correspond to a procedure dummy parameter? Well, under the hood, what an operator actually represents is a procedure. And so it's not ambiguous to the compiler what that operator is doing in this context. And you'll see it more in the examples in a minute. The instantiate also provides an only clause that allows us to do things like renaming just like we do for modules, and that can be very important to prevent name clashes when you're trying to instantiate multiple things within the same environment. And then here's a little kicker that has been controversial and has some strong pros and some strong cons. If you instantiate the same template with the same template parameters, it generates the same entities, not entities that are practically the same, but the same entities. And what this means is if a template is providing a derived type and somebody else instantiates it again with those same parameters, it's the same derived type. And you know that ordinarily in Fortran, if I have identical definitions of a derived type in one module and another module, as far as Fortran is concerned, those are two different derived types. So this is a little bit different than what you might expect there. So we're thinking of it as the template is really the place this is coming from. And so if you've instantiated it the same way, it's that same derived type. And what this is going to let happen is multiple packages can then use this template and make sure that they're talking about the same derived type then when they start interacting with each other. Okay, so let's start with a very simple example, swap. So here I've got a template construct named swap temple. It takes one argument, which is a type parameter, and it has no other properties other than the fact it's a type. So currently in Fortran, the way you have to say that is like this with type T, type : T, semicolon, N type. Bit verbose, but that's there to allow some extensions later on. We're going to declare swap to be public. That's a procedure that's going to be defined down below inside this template. And we're going to provide it an interface block to give it a generic name. And the reason I want to do that is that way if I instantiate swap for different types in the same environment, I don't have to use rename all over the place. This is just a friendly thing to do to your users when you're writing a template, is try to give it the generic name with a different specific name so that you can instantiate lots of times without that person have to give new names every time they do an instantiate of that template. All right, and then the implementation of swap itself is, of course, pretty boring. We declare two dummy arguments, x and y, both of type T, which is a deferred type, and a temporary variable temp, which is also type T, a deferred type, and then write swap just like the way you would anywhere else. And then on the right panel, you see how you would use it. So we can instantiate it. Here I've done it twice, once with real. It's going to give me an ability to swap two real numbers. And then another time with some derived type I've called my type. And since I've done that friendly little thing with the interface, of course, we don't have to give the swap different names. We can just call it twice with different arguments. So I've declared a couple real numbers, a couple of my type objects, and I can swap x and y, and I can swap T1 and T2. All right. Slightly harder example, find loc. So here we're writing a find loc that you give it an array of rank n, where n is now somewhat arbitrary, of any type T. And we have to also pass in a function equals. That's going to let us know whether or not two things that are of type T are equal. Okay, that might catch people off a little bit of guard. You can't make the assumption that the compiler knows what equal is for your derived type. Okay, so we've got to declare the interface for that equals argument. So here it's an elemental function. That makes it easier to use, but in other cases maybe it wouldn't have to be elemental. And then the implementation of find loc, we cheat because it's really easy to define find loc then in terms of the built-in find loc on logicals. So we use our equal operator to take our array of type T, which is declared right up here. I can't highlight it without causing but you see right up here, you take array as a type T array of rank n, and we can do equal to the value, which is a type T scalar. That returns a logical array of the same rank. And now we can use find loc on that. That's perfectly fine. It'll return the first element for which you got the true value, which is the one we wanted. And we pass along the mask and the result kind. Sorry, this is stolen from another example. Ignore result kind for the moment, and back, which comes from the other thing. Okay. And then I didn't give an example of instantiating that. Okay, here's an example of container, getting a little more complicated yet. The font had to get a little smaller. So a template has just the argument for the type. We want to build a container of type T. In this case, I did a vector. Those of you that know C++ STL, this is designed to be very, very much like an STL vector, but you can think of it as a list if that's a more familiar construct to yourself. So this template defines a derived type list. That's one of the things it exports. And a list has one component, which is just simply a growable array of elements. And it has a handful of type-bound procedures for manipulating that, for growing it and getting things out of it. It also exports an iterator, which is a means to allow us to iterate over the elements in a list. Now, in a list, you could argue this is overkill because if I can access the ith element of a list, I don't really need an iterator. I can use Fortran do loops. But if we're thinking this as part of a growing ecosystem of other containers where maybe I've got a tree where stepping through a tree is not quite so obvious, or a map, or a set, then an iterator gives us a very common way of stepping through all the elements of a container. And then you can imagine algorithms that are written just in terms of a container and an iterator and a type, and then doing all sorts of things with that without regard to whether it happened to have been a vector or a set or anything like this. So this is the way you're going to start seeing these kind of things coded in the future if we're successful. I've also thrown another trick into here. I've got an inner template. So I wanted my vectors to be sortable. And so I've written another template inside of it, sort, that takes one parameter. It's a comparison operation, less, tells me whether or not one number is less than another. Now, what I could have done is I could have made less a parameter on the original template, the outer template, as it were. But the problem is that some people may not care about the sort function. They don't want to use a sort function. They don't want to have to go define a less operation for their derived type. But the people that do want to be able to sort the vector, of course, do need a less operation. So what this lets me do is sort of create a class of additional procedures that need additional parameters. So some users would never use this, and so therefore would never need to declare this extra parameter. And the people that do need this don't have to declare the other parameters in addition. They get those for free by instantiating this template already in the outer environment and then re-instantiating the inner one. And I'll show you this on the next slide. Okay, so this first instantiate is providing me the container list and an iterator called iterator, and the sort template, but not the sort procedure, okay? And that's all for my type. Then I can instantiate the sort template with my less than procedure, and that gives me a ascending sort implementation. And I can instantiate it with my greater, and that gives me a descending sort implementation.
Where's the are you showing an iterator in this example?
Iterator was right here on the bottom of that first column. I'm not showing any methods being used with it. No, the much more detailed example is on the website that I talked about earlier, but nothing magic in there. Okay. So, well, actually, it does get used. Did I use it here? No, I did raw Fortran loops here instead of iterators, because again, for vectors, it's not a big win. But okay, so, and then you could just use it like any other Fortran procedure at that point. Let's see. So just to emphasize again why we want identical parameters to produce identical types with the same template. So suppose I've got two packages that both want to use this template for list that I provided a moment ago, okay? Package A instantiates it for integers and declares some variable. And then it says, oh, package B over here, it also uses integer lists to do interesting things, and it's using that same template out there. So I'd like to pass my thing to it. Well, that thing out there that's doing the instantiation to get that list type is a separate instantiation, even if it's identical code. If this produced two different derived types, both called list, we would not be able to interoperate. So this requirement that if you have identical parameters, in this case the parameters are identical, the integer in both cases, and I've got extra parens all over the place here, I apologize. This allows packages to work in this ecosystem. Now this is not the only way to do this. You could say that no, these are different types, and instead, any time this collaboration has to happen, you need to basically have an agreement about somebody somewhere is going to declare a module that does the instantiation that everybody's going to use. And that works well when you're within a small group or within something where there's a very natural ordering of packages, but oftentimes there's not. And if you look at the way this similar kind of technology is used, say in C++ STL, no, people just declare a vector of integers wherever they happen to need one, and they know that that's interoperable with vector of integers with anybody else that happens to have said that that's what their interface requires. So that's sort of the vision for why we push this. Okay, next bits are a little bit more subtle. Oh, I'm good, time. Weak and strong concepts is what they're called in other languages. We're using the term restriction because concept is sort of a bit vague from our point of view, and we can't use requirement, which would be great because that clashes with our role writing the standard. Requirement has a very specific meaning within the standard, so restriction is sort of our compromised term for referring to this. What we mean by a weak restriction is that the compiler needs to validate that the actual parameters you pass to an instantiate satisfy the interfaces that have been declared for that template. So that template said that the third argument was a procedure equal on type T, then the type that you pass better actually have, then the procedure you pass better actually be an equal type operation on T. Now what the actual meaning of that operator we don't care about, but it better take two arguments of type T and return a logical. And the compiler is going to check, and if you try to instantiate something using a type and a procedure that doesn't have that interface, it's going to come back and say that, no, this is not a valid instantiation statement. Okay. Now, this is sort of a no-brainer. Of course, the compiler should diagnose this one, but it's mostly I'm saying this by distinction to the next thing where it's not quite so obvious what you want. Okay, so the concrete example we have here is I've assumed my template has a function which returns a logical, and I passed in an operator plus, but operator plus on two reals returns a real, not a logical, and so this does not satisfy the constraint. And it will not, you won't get some obscure thing saying that you tried to add two reals and assign that result to some variable that you've never heard of deep inside of some template, which is otherwise what you might get with a poor quality thing. This is saying the compiler has no choice. It has to diagnose it at this level in a human meaningful way. Okay, strong restrictions. Here what we're saying is that within the template itself, the template can only use a certain subclass of procedures. And in particular, if it's going to use any procedures that involve the deferred types, those must be defined in terms of interfaces of procedures that have been passed in themselves as parameters, okay? And this has some pretty strong implications of things you can and can't do inside of a template. Now, why would you want to do something like this? The idea is that if you do this, you can now prove the correctness of a template without having to throw every conceivable type in the world against it and just wait for the day when some user gets really, really creative and finds some other thing that would work for it. So for instance, you might have a stray plus inside your template, to give an example. And it works for all the things you threw at it, because sure enough, plus works with reals, and it works with integers, and it works with complex, and you didn't think to try it with strings, and you didn't think to try. So you've got this interface up there that you told people it's going to work with their thing, and they come with their derived type, and it may even have a plus operation that's well defined for it, because the semantics of your template, of course, make it obvious you'd want something like this. But since you didn't specify that, they now have a type that doesn't have that plus operator exactly that way. It's going to fail, and it would fail in a fairly obscure way at that point, because now it's going to tell you some line deep inside the template, I don't know how to do this addition with the types that you provided. So this is a way for the template developers to have the necessary protections, to have confidence that their templates are robust against the variations that the template is intended to support. And I'm hoping I've said that clear. This is something we internally have a hard time expressing clearly. That may be the best I've done it anyways. Okay, to go along with all of this, these are not as crucial of features, but we think that they're sort of fairly nice enablers. Two more capabilities. The first of these is the requirement construct. This is a way to give us a reusable mechanism for interfaces that are going to appear in templates frequently. And sort of the classic one I've written right down here is you've got a binary operator that takes in two things of type T and returns a type T. So if you're going to have that, you're going to require operators in your template to be binary in lots of different places, then if we define a requirement like this, you can instead, and I'll show you how on the next slide, just use this as a shorthand for that, rather than having to type this long explanation out each time you have a binary operator in one of your templates. So what this looked like, here's an example using that. You'll notice there's no interface block here at all. Plus and times are procedures still, but they're implicitly, their interfaces are implicit in terms of the requires. And I left out a name. This is the problem with putting these slides together quickly. That slide should say, instead of requires operand T plus, it should say requires binary op. Actually, if you'll give me a moment, I'm going to go ahead and correct that here real quick, because that's just so confusing the way it is. Other typos were small, but this one is bad. Doesn't help there's no compilers yet, so I can't test any of this code before I show it to you. Even my editor doesn't help me because some of these keywords don't exist. Okay, so now you've seen this is more correctly done. So we've said that in order for this to work, you better give me something that looks like a plus in terms of interface and something that looks like a times in terms of interface. Well, they both look the same from our point of view, right? They take in two things of type T and return a type T. So I've expressed that very succinctly here, and then I wrote something that actually uses those capabilities. So you could write templates without these, but we think large and complex templates and packages of templates will be able to take these greatly. And Brad put together a fairly nice example showing how if you have, say, for instance, a less than operator, you could generate all the other comparison operators from that in a template, and then you can use those as part of further, that uses requirements, right? Yeah, okay, so there's an example there that more realistically does this, right? Okay, so now the dirty laundry I'm going to talk about, as opposed to some of the dirty laundry I'm not going to talk about. Deferred type parameters cannot specify components. Sorry, I said that wrong. Deferred types as parameters. So you're looking inside of a template, you've declared something to be a type parameter. It cannot specify components, the data parts of a derived type, nor can it specify type-bound procedures. Now, we can easily imagine that this restriction will be relaxed later in a subsequent version of the standard, but currently this is the way we're thinking. Part of the reason for this, just to give you some sense of why we decided this, is you could have very, very similar functionality in your derived type, but have spelled the name of your type-bound procedure differently. And there would be no way to use this template because there's no rename mechanism at that level in Fortran. So we'd either be wanting to spend some energy developing such a rename mechanism or encouraging people, well, you could write a template this way, but you shouldn't because you don't get maximal generality. Instead, what you can do is you could wrap your type-bound procedures and pass them in as an extra argument to the thing, and then your derived type can be new. And the nice thing is once you've done this for your derived type, it'll work with all the templates that just expect procedures, because you only have to wrap things once. You don't have to keep on wrapping each time. The next one on my dirty laundry list is template dummy parameters cannot be operators. We're only allowing them to be procedures. Part of this is just awkwardness. If you start looking at how you'd actually want to spell out the thing, you sort of get a funny thing where with existing Fortran syntax, you'd sort of have to invent a name to put inside the interface block, because the operator is sort of the generic name the way Fortran does it, not the specific name. And we really want the procedures arguments to be specific names in the context of a template. This too may evolve. Somebody may get clever or just push hard enough for the extension. But since under the hood, operators always refer to a specific procedure, operators can still be passed in from the outside. So you still get that power. And if you really want the expressiveness of an operator inside your template, you can, of course, always wrap the procedure arguments inside of an interface block in order to give yourself a named operator to then use. Okay, and then this last one is truly unfortunate, but I think it's going to stand again until at least the next revision. We're only now allowing value parameters to be logical, integer, and character. Before, we were allowing it to be virtually any type. And the reason that we made this restriction is because we realized that there are some painful subtleties about, well, how do we know that a derived type is identical in this instantiate to another instantiate? Well, we'd have to mandate that there has to be a comparison equally, but then there's no place to even put that in the specification. That could be solved, but there was one that was sort of the original thing that caused some hesitation. And then we started thinking, well, you can have floating point expressions, which are, in theory, are the same mathematically, but evaluate to different actual expressions. And so what would happen? So in one compiler, this would evaluate identically, and so you would get the same type. In another compiler, you wouldn't. So we decided that this was just a little bit too dangerous for us. And so we stepped away and we said, okay, let's go with the things which we have well-defined right now, what we know we mean when we say these parameters are identical, therefore the things that are generated are identical. Yeah. Okay, so there's a lot more work to be done. Subgroup in particular would like to find a better thing, like type T semicolon N type is an awfully verbose way to write things if we're not going to allow components and type-bound procedures. On the other hand, keeping it like that lets us stick that in later on, so that may stay the way it is. Boy, I got cut off even right in this one. So the draft of the formal specifications is nearly complete. There's still several things which we know need to be done, and a lot of things which we suspect we're going to get pushed back and we need to go think about some more. Discussions this week will be very revealing, I think is the fair statement. I'm probably very naive. This is the first time I've ever been on the committee throughout birth to death of a, sorry, that's the wrong way, but. Sorry, conception to birth of a new feature. So I don't really know how hard it's going to be go from specs to syntax. My sense is that's going to be relatively straightforward. Edits, on the other hand, I have seen enough difficulty with edits with features that are far smaller than this to be aware of how hard this is, especially since, very few people on the committee really know where all these different things are expressed in all the places. And so it's oftentimes a really interesting hunt just to go find, even when you know the kind of thing you're looking for, to go find all the places that need to be touched. And then each time you do it, the danger of actually doing it wrong and making things worse rather than better. So yeah, real hard work ahead of us in the next few years. If you would like to contribute, there's a GitHub generics thing, open issues there, contribute code examples if that aligns with what you want to do. We meet as a subgroup, but that's open to anyone. It doesn't have to be just members of the Fortran committee itself. We generally have been meeting every week. We start meeting every other week, and then we decide we have too much work to do, and so we start meeting every week. Because of the fact we have people in multiple time zones, it pretty much means that we've been meeting at noon Eastern time. So if that's a good or bad time for you, you can take that into account. And of course, there is the J3 mailing list, which you won't be recipients on, but if you have suggestions about what Fortran could do, you can, of course, mail to that group, and that will at least reach our attention. Other people in the room can probably give you additional ways to contribute. And then just some quick references. Anyway, and good, I left plenty of time for questions. Yes?
Go ahead.
Oh,
Yeah, go ahead.
So every question that came up from me, you answered in a subsequent slide. So I didn't think I had any questions until you put this one up,
okay.
because there's no subsequent slide. So how does mathematics of arrays relate to this?
I ran out of time to try to figure out how to word this in. So if you go back to what I was doing with the at notation, that is one particular operator that was introduced in mathematics of arrays. And there are other things in mathematical arrays which Fortran already has, like the notion of a slice of an array, and even to some extent the transpose of an array. But there are other operators in there that there aren't direct Fortran analogs, and it might make sense for Fortran to sort of study that paper and introduce the remaining machinery from that paper for maximum generality of rank agnostic things. I don't think it's going to be particularly hard. It was one of the things we always meant to go back and do, but the existing work has really been a distraction. It's orthogonal to the rest of the stuff we're really doing with generics, I think. And so I'm hoping there's still room within the Fortran 2020Y to add that in as an additional topic for either the generic subgroup or some other subgroup that might want to own that. It might make sense for that one to go to data, for instance. Yes?
I'm going to turn this mic on. There's a question online from Amir. In the find lock example, why would one need a rank parameter argument? Isn't that implicitly realized in the 202X standard? The example passed fast, so I may be wrong.
You'd really like to think so. The problem is, in order to write the procedure without the rank parameter, you have to use what's called assumed rank. And there's not much you can do then with the assumed rank, so all those other expressions we wanted to do aren't possible. Now, a more complete example could bridge the gap. What you can do is provide the outer one without that parameter. And then inside of the outer template, we could instantiate for all of the allowed ranks. And then we have an inner template that does have the rank parameter. And your example's up to date. So Brad has an example on the GitHub site where that has been worked out more completely in that way. It just doesn't fit very nicely on the slide, and that wasn't the primary point I was doing. So yes, you can, but then you're obligated to overload on behalf of the users because we can't do for technical reasons, it just doesn't quite work the way you'd like it to. Yeah. Okay.
I have another question online from Patrick. Will there be Fortran template metaprogramming?
I think in the words of our outside consultant, not if we can help it. We're trying very hard not to let that be possible because we think that's a source of difficulty, complexity, and bugs. I don't know. Magna, did you want to say anything more about that? Why we don't want it?
I think it's better served with a specific.
Yeah.
Yeah, if you can use that, that'd be great, just so they can hear you.
I think that metaprogramming is better served by a specific feature for metaprogramming and not by accident in the template feature.
Okay.
Anybody else?
You didn't have an example, and we can talk offline if you want to defer this, but I hate iterators in C++, and so I tried not to use them. And so in C++ 11, you can do for, and the iterators are kind of hidden in the syntax. And do the iterators kind of work like while, began less than end sort of thing?
Yeah, well, iterators are just provide the hooks and you still use a Fortran loop outside. So you basically define begin and end, and then you do while iter not equal to end, and then you have to make sure you do the iter next somewhere. And if you have a cycle statement, you're in trouble because you'll skip your iter next. So yeah, no, something maybe generics should look at next would be to make something that meshes more fully with the existing do constructs. Yeah, that's been talked about. We just haven't really got to it, but yeah.
Oh, I have a question on your first example. You had like the explicit interface for overloading. Does that restrict the type? Like if you only wanted your template to be used on, I don't know, integers and reals, can you say not strings?
No, and we have had some discussion about providing mechanisms to somehow restrict which types of things are it's applicable to. But the sort of the approach we're trying to take is, if you can express the template in terms of a deferred type and procedures that work on that deferred type with the appropriate things, why would you not want to allow somebody else's type that comes along and satisfies those things, right? Now, a lot of, if you require there to be, you know, something that looks like a plus operation, that is going to rule out a whole bunch of types all on its own, right? But somebody still might come along and, wrap the concatenation operator for strings and make that plus, and it may still work very nicely with your algorithm. So it's not to say we won't ever do it, but the current release, we won't be doing that. But it's possible later on you'll see ways in which we can say that this should work for only the subset of kinds or this subset of types, like, you know, numeric is the one that comes up. Our guidance, again, is generally this is not a thing you want to do. You want to write your templates for maximal generality. Okay. Yes.
I would say an argument for restrictions would be, let's say I write a template for matrix-matrix multiplication. If someone instantiates that with integer star 2, the code would now have to take extraordinary, extra effort to not overflow and be trash. Whereas if you can say, I'm only going to accept types that are big enough to not spill most of the time, then you could write code that would be a lot less awful. So it'd be good to be able to write a matrix multiplication template and say, no, you can't pass this thing a type that only has, a range of 16,000.
Anybody else in the subgroup have a strong response to that? I mean, one approach, of course, in that particular case would be you don't expose the template itself, you expose the cases that you do want them to be able to use by instantiating yourself and then providing that module, right? But, it's sort of a really interesting thing because, I want to write matrix multiplication to work with my type or blocks of matrices and stuff, and it's going to be really hard to say that, oh, I can't do low precision integers and still allow all those other cases that I do want. That would be hard to express, I think. Yep. Anybody else have a thought on that?
So one of the things that we've been thinking about when we're talking about like strong concepts and stuff like that, there are certain ideas that you'd like to be able to express that you really can't express statically. Something like the plus operator should be commutative and associative. But you can't express that in a static way. Like the compiler can't check that that's actually true unless it actually does a whole slew of testing that, yes, in fact, A plus B plus C equals A plus, swap them around or, put the parentheses in different places. So this is one of those things where it's like, yes, you'd like to be able to express it, but it's really hard to express it in a way that's statically checkable.
I have one other thing that's still to the side, but maybe opens a door. One of the concerns I had is, okay, so I've got my generic matrix multiplication algorithm. I don't want people to use it on intrinsic reals because it's going to be far from optimized. I'm not going to, it's not going to be unrolled in any magic way or anything like this that the optimized BLAs would. But so the idea then is that users would not call my template for those things, right? Now they might pass in, for a block matrix case, they might pass in the optimized map-mul from the compiler as the block operator within the block matrix multiply. So we've got that part worked out in a reasonable way, but they could still instantiate the slow map-mul if they're so inclined. So there's a little bit of an education to the user base about if you're doing this, understand that that's not always the right way to do it.
Question, do you have the ability to know the type that was instantiated inside of the thing. Like in C++, I can say, type name T, and then inside of the template I could write, I could say if type of capital T equals type of double, throw, I don't allow you to use doubles because I'm a jerk. Could you theoretically put, if the type that you instantiated on matches a type that I know, do something?
We have discussed things in that direction, basically statements which will be evaluated during the instantiation that can be true or false that would invalidate that particular case. For the moment, we've steered clear, but that has to be re-examined, I'll certainly grant. Yeah, right now we don't have that.
Because I think that would be something, so you're exactly right, generic matrix multiplication is horrible. But if I know that you instantiate it with real 64, I can say, if it exactly is real 64, call BLAS. If it's exactly real 32, call BLAS. Otherwise, there would be other things. So I could specialize all of the cases where I might want to specialize, but I would have to know inside of the thing that the user instantiated it as a specific type.
Right. When we started, I very much expected that was sort of the kind of thing we were doing, but Magna might want to address that one in particular because he's responded to that several times about why that's not a good idea.
One thing is if you introduce template specialization matching, which C++ has, you're introducing vulnerabilities into the template mechanism. And I think that is something that would show up in the vulnerabilities subgroup if they really wanted to discuss that deeply.
You're introducing what?
Vulnerabilities.
Vulnerabilities. Somebody can hijack your template and do something else from what you were thinking. And the other is a maintenance issue, because if you don't have access to that template body and you have introduced another type which has very good optimization properties, you won't be able to case that inside the other people's template. So you will still have to manually from the outside be aware that I'm now calling a generic suboptimal matrix multiply rather than my specialized matrix multiply. So I think you're just postponing a problem people will observe later on if you try to do that too early. But
Code that isn't on that they can't read it. Sorry, I don't.
so, yeah.
That's an interesting count.
Yeah, so it is sort of, can you do things later on with somebody else's code if you don't have access to the internals?
I think it's quite easy to discover what the real type is. You just call a class star, call a subroutine that takes a class star argument and do select type and go, hey, I've got double precision real here. End of, game over for the hiding the type from the template writer.
That's
you
true.
Can't do it.
Yeah, good point.
I have a question from someone online. Mark says, in your list_TMPL with SOAR_TMPL inner template, if you are using two different templates that both have an inner template named SOAR_TMPL, can you use a rename mechanism to distinguish
Yes.
the two different sort templates?
Yes, it would look just like you would expect from a use statement. Instead of instantiate, you'd have use statement, but you do a comma only, the new name points to old name. So that should make sense to them, even if it doesn't to everyone. And we have more complicated examples where we have to do that. The Matt Mole example online does exactly that, for instance.
Oh, I turned it off yet. Sorry.
Okay, let's thank Tom for making this time and for this beautiful presentation. And thank you, Tom.
Well, thank you for having me.
Yeah.